Hi everybody, this is Tor Storley and I am back with another video. So I'm back in my GitHub repository for the financial functions R package, and I made some changes here, and there is now, as you can see here, I added something called a batch function. And what do I mean by a batch function? Well, when you are calling my package in R using the regular functions like internal rate of return, the IRR function, or the XIRR, where you have dates on different intervals, or the NPV, when you have a lot of cash flows, you might want to consider passing it into Rust in one go instead of calling it one by one every time. So in this video, we will look at these new batch functions, and I will also demonstrate some speed tests that I did on the R package and against DuckDB's community extensions that has the same 55 functions. Now, there's no batch function in DuckDB because it's not needed because it works on a column format. The IRR function and those functions are scalar function in the R package, but using this IRR_batch method, you can pass in a list. So it will pass everything over to Rust and it will execute the calculations there, so it's much more efficient. I updated my README file here. I already went through this in the first video, so you can look there for the information here. When you get down here, you can see there's batch function section now. And again, like I said, it's for processing large numbers of calculations. So if you have some testing you want to do against 10,000 rows, 100,000 rows, or a million rows, you can use the batch function for certain things, not for everything. You can see here I got for internal rate of return, the internal rate of return when you have dates that are at different points in time, the NPV, and the modified internal rate of return, also payment, and price curve also for bonds. Okay, you can see bond prices across a yield curve. Here is some examples of how you can use it. You can see here you are applying between 1 and 10,000 samples here. Here is the numbers, and then you are calling the system time so you can figure out how long it takes, and then you calculate the stuff. I have a couple of examples I'm going to go through in another document that I generated. So the first thing we want to do then is we want to go and actually look at these financial functions. And again, you can see here over on my right-hand side, there is this batch functions. By the way, this document is kind of showing you how you can use these different functions. And you can also shows you how you can use it with dplyr. Here is the batch function section in this document. And you can see here, I give you a couple of examples. In this case, how do you run 10,000 random investment scenarios? Here is one for NPV. And you can see I'm calling the NPV batch function. And here is for bond prices or the yield curve. And you can also compare like multiple mortgage scenarios at once by using this payment vector like this. Here is example of an internal rate of return for multiple projects. Now, in this case, it's just a few of them, as you can see. There's only like 5 of them or so here. So that's not really a test for speed or anything. But I have other examples where you have that. So you can look at this. These are the examples. And also, I have a third document that I added. So in case you want to go to these, you can just navigate on the top here. There's also a document for speed benchmark. And this is the one I will cover in this video. The bottom line is you want to figure out which is the best method to use for your scenarios. What are the chances that you're going to have a lot of cash flows? Well, it all depends. But if you are just going to use it for casual usage, like maybe 1,000 cash flows or what have you, you know, the original code will work just fine. And in this document, I did a few tests here so you can see it. So there's really more than 55 Excel compatible function, but it's still the same function. It's just improved with the batch. I just listed as 55. In the context of R, it's using the apply function. So if you look down here for this first benchmark, you can see here that The Rust internal rate of return calculation itself takes about approximately 1 microsecond. And a small overhead dominates, okay? Because you have to call it over and over and over again. So if you can pass it all in at once to Rust, that's preferable, because otherwise it's going to be slow in the transit because you have to pass it into Rust every time. If you use 10,000 calculation, you use this sapply function in R, then you're going to see that you can run this kind of code. And if you do, you're going to notice it's not much of a difference for such a small amount of data. If you go into financial functions R here on my GitHub repository, and you go to vignettes and you open the speed benchmark.rmd, you're going to see this code right here. This is the code that calculates the pure R version of the internal rate of return. So the difference between that one and my version of IRR is that my version uses Rust. So you have to pass it to Rust to compute it. Here, you just run it in R, so it's very efficient here. But, it's only one calculation. This is the internal rate of return. But if you look at the layout here of the Newton, okay, as you know, Isaac Newton, he was working a lot with calculus and so forth. So in here, you will take derivatives. Now, there is a Medium article here you can read if you're interested of the details of this. So you can see the Newton's method here. The method here used is to find the absolute minimum, meaning when the internal rate of return rate makes the net present value equal to 0. So the whole idea here is to trial and error a rate and check it against this curve and see if it's going negative or positive. So you might undershoot, you might overshoot. And if you overshoot, you got to dial it back. So you want this horizontal line, meaning as close as 0 as you can get, because that's the absolute minimum. So that's what our algorithm is trying to accomplish by trial and error these different rates and go for where net present value is closest to 0. So you have to use iteration. Now, one thing that you see here is this first part of the algorithm. It tells you that you have a vector of cash flows, say negative 70,000, 12,000, 15,000. So you have a negative number and you might have one or more positive number. And you have to have that in order for this to work. So you start with your cash flows, which might be one cash outflow and many inflows. Your first rate you're going to try is a guess rate. So you can try 10%. You say, once you do these iteration, if you get close to this, the tolerance here is, as you can see, it's a negative to the negative 10. So that means like 9 zeros and a 1. So it's almost 0. Okay. And the max number of iterations you want to run is 300. All this is doing is that says that, hey, you can't have less than 2 cash flows, meaning one negative and one positive at the minimum, okay? You have to have at least 2 cash flows. One has to be negative, one has to be positive. Then what you do is you calculate how many cash flows you're going to have. You create a sequence based on these cash flows. So it'd be 1 through 7 because you have 1 cash outflow and 6 cash inflows. In order to index it back or dial it back, you basically, by subtracting 1, you want to bring it back to 0. So you will have 0 through 6 cash flows, in other words. So the time starts at 0. And why? Because the initial cash outflow happens right now. So you want to indicate that it's not going to happen a year from now. It's happening right now. So that's why you use this 0. And the reason is because you're going to be calculating this stuff, okay? You're going to raise it to a certain power of it, like here. So you start with a power of 0 here through 6, okay? So you're setting your R initially to 0.1, which is up here. And then you start your for loop because you have to iterate. This is just a placeholder for whatever the value you're on is, okay? It's just the syntax of this code. Here is the sequence length is going to be the max number of iterations. So you're going to repeat this up to 300 times. And typically, the internal rate of return based on this method will converge about 5 to 20 iterations. So you're not going to probably get close to 300. You want to calculate the discount factor by stating this, which basically means 1 plus r. So in the first instance, this will be 1.1 raised to the power of 0. Second instance will be 1 plus 0.1 raised to 1. 1 plus 1, 1.1 raised to 2, and so forth and so forth. So you'll have basically a t0, you'll have 1 when you raise it to the power of 0. And t1, you will have 1.1. And t2, you'll have 1.1 raised to the power of 2, so it becomes 1.21, and so on and so on and so on. Then you compute the net present value here. So by taking the cash flow divided on the discount rate, then you sum it all up. Okay, that's what the NPV is doing. Then you take the NPV, you calculate the derivative of it in respect to R. So that becomes this portion here. If you have any interest in the derivatives, check this out and get a feel for what that is, or do some additional research. So once they get the derivative, you'll be guarding against the flat derivative. So if a derivative is nearly 0, the curve is flat at this point. So by dividing it, it will give an infinite step. So at that case, you have to return NA because you can't really do it. Because, you're dividing on 0 is infinite, right? You can't do it. Then you update the new R here. And then you create the new guess. If the guess barely differs from the old guess, meaning it's less than 0.0000001, then you have converge. So that's what you're returning, okay? All right, anyways, you get the idea. So if no converging happens, then you return an NA. And that's what this is doing. So it's pure R code and is using this Newton-Raphson internal rate of return method. Okay, I just want to point that out to you. Here is the benchmark for 10,000 calculations. So here is when you call Rust via this R sapply function. And you can also run this pure one in R like this. But notice, it's not a lot of change here. 0.78 times versus 1 time. So it's minimal. So it doesn't really matter, you can call the regular function, in other words. Here is when you have 1,000,000 calculations. So here you can see we are setting a seed, and the reason you do that is so it's repeatable. So every time you run these numbers, you get the same result. So the first thing is to set up a variable that's going to hold 1,000,000. It's just a number for now. And then down here, we're going to pass in this n large, or the 1,000,000. It's going to generate a sequence between like 1, 2, 3, 4, up to 1,000,000. So it's just like a counter, if you will. So it's going to be repeated operation 1,000,000 times. Here is where you're passing in. So for every one of these 1, 2, 3, 4, it's going to pass in this to this function here, okay? This I is not used, but it's a way you can set up this function where you create a sequence, how many times you're going to run the function, and then you run the function per step, if you will. And you use this lapply because it's much more efficient than if you use a for loop. So it's kind of optimized in R to use this lapply to pass in how many times you're going to run this function. What we're looking at here is that the lapply is going to apply this function for every element in that sequence, 1, 2, 3, 4. So it's going to call it for every one of those, and it's going to return a list of 1,000,000 results. So you can think of it as a for loop, and you collect each result into a list and return it. Now, this C minus sample 50,000 : 200,001. So what that does is it generates one random integer between 50,000 and 200,000. And then you prefix it with a negative because it's going to indicate this is the initial investment. So for example, one value might be I don't know, minus 123,456 or something like that. So that's that part. So that creates the initial investment, and then you're going to create 6 cash flows, as you can see here. If you look at this run if, so basically what it says is it stands for a random uniform. So it's a uniform random numbers from a uniform distribution. So that means that every number in there from the min, which is 5,000, to the max 50,000, has an equal chance of being picked. So that's what that does. So it's basically going to create your cash inflows. So this is the cash outflow. These are the 6 cash inflows. And when you combine it, you're getting 7 total. And that's basically what this code is doing. And then again, down here, you simply pass it into the batch function here, this list that you created up here. And then you calculate the internal rate of returns and get the whole batch back here like this. So if you look in the librs that is located under this repository source, Rust, source, and there's a librs file. If you scroll down, you can see this is the code for the calculation of the batch internal rate of return. And notice you're passing in a list, as you can see, but you're returning a vector of float 64 from Rust. So that's the return that comes back. So that's what this T batch large is getting back, a vector of 64 from Rust that is translating into the R equivalent. Okay, so that's kind of how that code works, and there's a few examples that uses these techniques. So I'll let you look at the rest of them. So here, if you look at the IRR batch method, where you make only one call by passing in all 1 million cash flows to Rust in one go, then you will get 1.7 times faster than if you ran it purely in R. In other words, you had a function that can calculate it directly in R without using the supply, obviously. You can see the time it takes there, 5 seconds, and this is 9 seconds. That's for 1 million calculations. Here is a third kind of benchmark. If you want to calculate bond price versus yield curve, you can do it this one. And you can see when you run that kind of calculation here, 2.6 times faster if you run that price curve batch functions. In other words, the one who passes in 100,000 yield levels, and it calls Rust only one time because it passes everything in at once. If you use the pure S-supply in R, the scalar one, we have to call it one time per 100,000. So in other words, 100,000 times you got to call it. Then you can see that was the measurement against this. So by having the batch method, it's 2.6 times faster than if you run this pure one. So if you have a lot of records, the bottom line here is use the batch method if it's available. Here is just another chart, you can see it. And this is benchmark 4, where you actually use the DuckDB CLI. If I run it against my community extension for it with the financial functions, this is for the bond yields. I'm not going to do this one because I want to just get to the point here. What if you want to run the internal rate of return for 1 million random cash flows using SQL? How will that behave? Well, how do you structure it? Well, you can set it up like this. So let's just open up DuckDB CLI and take a look at this. Okay, so in order to do that, I open up a regular command prompt. Okay, so now we're in. Notice I'm using version 1.5.2. So in order to run the community extension, I have to load it. So I can use this command here. My extension happened to sit because I want a short path. So I say, put it inside this test finx folder on my temp or the TMP folder. And that's the name of the extension. Okay, so now it's loaded. What I can do now is I can test that SQL query that we have. So I'm going to copy that over so we can take a look at it. So I'm going to run the first part of it so you can see how this works. This is the with raw as, and this is the select statement in that query. So I'm going to put just a regular query here so you can see what it does. Notice I'm selecting and I'm using random numbers here. So it's going to take whatever this cash investment is, and then it's going to calculate a random number times 150,000 here. So all of these cash flows here is going to be computed 1,000,000 times. So let's see what that looks like. So I'm running it, and as you can see, it ran pretty fast. And that's the first part of that CTE. This is the 1,000,000 cash flow here, you can see it. Okay, so that's the first portion of that query. The second portion is this one. So let me copy this down and fix it. So let me clear this and let me paste it. All right, so now I will have this with statement. This was the first part we ran. And the second part is going to be this. And why do you do this? Well, in my DuckDB community extension, we passing in these cash flows as a string. So all the numbers separated by comma in that cash flow. So if you have 5 numbers, let's say, or I can use this example. So here you got one investment, 1, 2, 3, 4, 5, 6 different cash flows you can see here. So BCF0 is the investment, and these are the cash inflows. And those guys are going to be passed in as strings. So when I do that, you can put this comma between each one, and you make it into varchar. So you're prepping the function for the actual execution of it. So what happens when I run this now? It takes a few seconds, I guess. So as you can see here, it did compute this right here. So that's internal rate of return calculation. So it's pretty fast for 1,000,000. And one of the reasons it's fast is because it's pre-prepped with string notations around it. So it's a varchar. Let's finish this query. So I'm going to copy the whole thing in, and we're going to run it one more time. So, and paste this query in. And this query is part of the documentation, so you have access to it. So here you can see it ran in 8 seconds, as you can see here, using this method in the CLI. However, is it that fast? Maybe not. So if you look at the results now, this was the DuckDB CLI, as you can see here. And the one we did was this 1,000,000. We didn't do the bond prices, but you can see it here too. So it ran when this was recorded, it ran in 7.75 seconds, okay? And you can compare it to the batch here. The batch actually was faster, as you can see. Now, why is that? The reason is that the CTE has to be parsed. All those things has to be parsed, the queries and everything, and has to be prepped. Therefore, it uses more time. Can we improve on that again? Well, yes, you can. The trick is to stick all these cash flows into a table like this. So if you do that and prefix it like as a varchar in the table and then call it, we're going to see how well it does. So what I'm going to do now, I'm going to create this table. Okay, so I'm copy that, and let's bring our DuckDB over again, bigger, and paste that query in. Here we're going to insert all those records, and you can see it inserted 1,000,000 records in here now. What does it look like? Well, let's take a look. I might have it in my documentation. Let me take a look. So that's the first part. So the second part is this one here. I want to run this query so I can see how fast it runs, okay? All right, so let's run that query and see the result. So I'll put the timer on. It's going to do a bunch of counts, and it's going to find the min result of those 1,000,000 calculations and max and the average from those cash flows. And there it goes. Notice this, pretty fast. Okay, so now it's time to check out how well these different things work. Okay, so if you look here, if you do 1,000,000 internal rate of return calculation and you eliminate the query time overhead, then the DuckDB table query where we inserted the records and made them into varchar strings and then passed that to the community extension internal rate of return function that is in Rust. You're passing the whole column in, and you're passing in 1,000,000 records, and this will be 1,000,000 calculations. And notice this is pretty impressive. 1.23 seconds to execute 1,000,000 internal rate of return functions. Now that's pretty fast. That is really fast. Here you can see the comparisons. If you do it for the pure internal rate of return method in R, then it takes about 10 seconds almost. If you use DuckDB with the CTE query that has to be parsed and randomized, because you have to randomize the numbers. Then it runs in about 7.75 seconds. If you use the internal rate of return batch, that's pretty impressive too. That ran in 5.5 seconds. But of course, you can't match the speed of C++ together with Rust in an optimized environment for column storage like you find in DuckDB. So what does this tell you? Well, it tells me that you need to kind of figure out what is your case scenario that you're trying to solve. If it's very few cash flows, stick with the regular one. It doesn't really matter much. It will run just as fast as these other ones. If you have to do a lot of crunching and if you have to create a bunch of scenarios, and there's a lot of records, you might want to try out the DuckDB CTE maybe. If you really need speed, you probably should pre-prep the data into a table and run it in DuckDB in the community extension there. That's what I had for you today, and this is the second part of this video series, and I hope you like my videos, and if you do, give me a like and consider subscribing to my channel. Be fantastic. I'll see you in the next video. Take care, everybody. Bye-bye.